Hi, in this video we're going to talk about something called the chain rule. So thus far you've talked about derivatives. You may have derived something called the power rule, or maybe the product rule, or maybe the quotient rule. But the chain rule is really the most important rule of them all. The chain rule tells you how to differentiate compositions of functions. So let's say we wanted to take the derivative of f of g of x. How would we do this? Well, a long time ago, when people much smarter than me started inventing calculus, they looked at this and said, well, there's no obvious answer to this at first. But then one of the inventors of calculus, Leibniz, said, well, if we look at this, it should be that this is going to equal the derivative of f with respect to g times the derivative of g with respect to x. Now this notation may look a little funny, so a more familiar way to write this might be f prime of g times g prime of x. So what does this mean? What is this telling us to do? It says that when we have a composition of functions, when we take the derivative, we want to take the derivative of f as if it was just a function of x, but then leave g as the argument, and then multiply the whole thing by the derivative of g. So let's do an example and see what this really means. So let's say we want to find the derivative of x squared plus 2x plus 4 all raised to the 1/2 power. So what we need to do is we can look at this as a composition of functions. So let's say that f of x equals x to the 1/2 and g of x equals this inside part here. Okay, so we can recognize this now as the derivative of f of g of x. Okay, well the chain rule says that this is the derivative of f with respect to g. So the derivative of f, as you know from your power rule, is 1/2 x to the minus 1/2. So we need 1/2. But instead of x, we have f prime of g. So this is g to the minus 1/2 times the derivative of g. Well, the derivative of g is just 2x plus 2. So we multiply this by 2x plus 2. Well, we know what g is, so we can plug it in. So we have 1/2 x squared plus 2x plus 4 to the minus 1/2 from here, all times 2x plus 2. So we can rewrite that a little simpler as 1/2 1 over the square root, because when you have a negative exponent, it's just the exponent in the denominator, of g times the derivative of g. And that's our answer. So this is how you would take a derivative when you have a composition like this. However, having to recognize this f and g and write it out like this all the time can be a little cumbersome and be annoying to write out. So let's see what we actually did here. If we look at this, we can see that when we take the derivative, what we're basically doing is leaving the inside part alone and just worrying about it as if it was x here. So if you would take the derivative of x to the 1/2, as you can see here, you would get that. So all we're doing is we're taking the derivative, leaving the inside alone. And then we just come over and multiply by the derivative of the inside. So that's what you can think of the chain rule as. You take the derivative, leaving the inside alone, and then multiply by the inside. And this corresponds to this fancy notation up here, the derivative of f with respect to g times g prime of x. So let's do another example. Okay, so we want to take the derivative of, let's say, 1 over x squared plus 1. Now, you could use the quotient rule here, but why would anybody ever want to? So let's use the chain rule. So to use the chain rule, what we do if we rewrite this, is x squared plus 1 to the minus 1. Okay, so when we want to look at the derivative, we want to say, well, we have something to the negative 1, but it's not just x. So what we're going to do is we're going to take the derivative, just leaving this part alone, and treat it as if it was just x. So how do we do that? Well, we know the derivative of x to the negative 1 is negative, so leave the inside alone, and then you subtract 1 from the exponent. Okay, but the chain rule says we have to multiply by the derivative of the inside. So we get 2x. And this is, in fact, our derivative. Okay, so again, leave the inside alone, then multiply by the derivative of the inside. Okay, so now we're going to look at an example that tends to trip up a lot of calculus students. They don't exactly see why this should be true, but all it comes from is the chain rule. So let's say we had this. Let's say we had y squared plus y equals x, and you were asked to find dy dx. Okay, so it's not obvious how to start here, but before we even go on, let's recognize that this y is really a function of x. So y is really y of x. We just write y so we don't have to write this extra part each time. So what we're really looking at is y of x squared plus y of x equals x. So all we want to do is we want to take the derivative of both sides. So let's do that. So we have d over dx of this side and the derivative of x is, of course, 1. Okay, so if we look at this, we need to treat this using the chain rule because we have a composition of functions. We have a function here, and then we have a squared function on the outside. So we take the derivative of this just as we would the derivative of x squared, but then we have to multiply by something because the chain rule says so. So if we look at this, we leave the inside alone, and then we multiply by the derivative of the inside, which is, of course, the derivative of y. Over here, this one's much easier because it's just the derivative of y. So now we have a dy dx in our equation, which is exactly what we wanted to solve for in the first place. So what do? We just factor out a dy dx from both parts. So we have dy dx times 2y plus 1 equals 1. So we're going to divide by this, leaving us with dy dx equals 1 over 2y plus 1. And so this is the slope of the tangent line to any point on this curve. And we call this implicit differentiation. We call it that because y has implicit dependence on x. You can't see it, so it's not explicit, but we know it does depend on x. We call it implicit differentiation. And basically all you do is you take derivatives, but you always have to remember to add this dy dx term when you're taking the derivatives because of the chain rule. Okay? So now we're going to do one last example, and it includes this implicit differentiation. And the problem is, if you're given the unit circle, the equation of the unit circle is given by x squared plus y squared equals 1. I want to know the slope of the tangent line at the point square root of 2 over 2, square root of 2 over 2. So I want to know the slope of the tangent line right there. So the slope of that line. Okay, so if we want the slope of that line, what we really want is dy dx evaluated at this point. Okay, so in order to do this, let's find dy dx. So in order to do that, we'll just take the derivative of both sides of this. So we have the derivative of x squared plus y squared equals the derivative of 1. Well, the derivative of 1 is 0, so we get the derivative of this part is 2x plus 2y dy dx from our chain rule equals 0. So now we just subtract over this side to here, and we get 2y dy dx is equal to minus 2x. Well, the 2's cancel, so we're just left with dy dx is equal to negative x over y. So there's our derivative in general. So if we want to know the derivative at this point, square root of 2 over 2, square root of 2 over 2, so basically at 45 degrees, all we do is evaluate at that point. So dy dx of root 2 over 2, root 2 over 2, is negative square root of 2 over 2 over square root of 2 over 2, which this, of course, is equal to 1 because you're dividing both of the same thing on the top and bottom. So we get the slope as negative 1. So at this point on the unit circle, our slope is exactly negative 1. So that means it's parallel to that line. So that's the chain rule. Chain rule is the most important rule of differentiation, and you will use it countless times throughout your calculus career. And if you understand it, you'll be very well prepared for the rest of your calculus courses. Thank you.